6.4, use inverse functions. This illustration actually sums up what we're going to be doing today perfectly. So I'm going to refer back to it a couple times. But what I'm trying to say in this section is that we put some input into our function machine. Say we put apples in and we get out lemons. We do something to it and we get out lemons. This is like putting in an x and getting out an f of x. Now, we are going to put the lemons into the f inverse machine. And when we do that, we get back out our original thing, our x. All an inverse relation really does is interchange the input and output values of the original relation. So I'm kind of saying that you switch the x's and y's. When you switch the x's and y's, so instead of having 0, 1, 2, 3, 4 as the x's, the inverse will have those same things as the y's. You see that? So that's why, let me color code it. That's that. And then the original y values become x values in the inverse relation. So this right here is key, that you switch the x's and y's. And in doing so, wouldn't the domain and range just be swapped? You're making all the x's y's and all the y's x's, so that's swapping the domain and range, right? One additional point that I want to make is looking at this picture here. You'll see that the original relation is the blue dots and the inverse relation is the red dots. And in this example, it's not super obvious, but when plotting the original function and plotting the inverse function, it is simply a reflection of the original function over the y equals x axis to get the inverse function. So keep that in mind, that a reflection of the original function over the y equals x axis gives us the inverse function. Now they're asking me to find the inverse of y equals 4x plus 2. Well, I just said that the inverse is just swapping the x's and the y's. So all I did was swap the x's and the y's. And so now let's just solve for y. So let's subtract 2. X minus 2 is equal to 4y. Let's solve for y by dividing by 4. Divide by 4. Divide each term by 4. And we get 1/4 x minus 1/2 is equal to y. In other words, y equals 1/4 x minus 1/2. And we're actually going to be writing this as the inverse of f is 1/4 x minus 1/2. And I'm about to introduce this in the next thing, but I just want this in your notes because that's how we're going to be writing it. So f and g are inverses if f of g of x, or you could also do g of f of x, pops out just x itself. So let's look back at our illustration. So you put an input into the f machine. You get out the lemons. And then you put that into the inverse machine. You should get back out the original thing. So again, I'm just saying in this one that f and g are inverses if when you put it into one machine and then you put it into the second machine, you pop out an x. And you can do it in either order. The function g is defined by f inverse reads as f inverse. So in this example, we're saying f and g are inverses. So g should just be defined as the inverse of f, and the shortcut is f inverse. Note that this -1 here is not an exponent. And that's really important. This is just notation. So whenever you see f to the -1 of x, that does not mean a power. We call it f inverse, and we don't say f to the -1. It is not f to the -1 power. It is f inverse. Important. So I really could rewrite all of this stuff in something that I think makes even more sense. If we do f to f inverse, we get out our original. And also, if we do f inverse to our original, we get out just our x. And so that's exactly what the illustration on the first page is saying. These two statements are synonymous. Verify the two are inverse. Well, we just learned that the two are inverses if f of f inverse equals x and f inverse of f equals x. So let's see if that holds true. Let's first do f of f inverse. Look at the inside function first, and that is 1/4 x minus 1/2. So I need to do f to that. All this means is that everywhere in my f function where I saw an x, I'm going to replace it with this guy. So I have 4, instead of an x, I have this guy, 1/4 x minus 1/2 plus 2. 4, this guy plus 2. 4, this guy plus 2 equals, now let's just distribute that 4, so we get x minus 4 times 1/2 is 2 plus 2 equals x. Beautiful. We proved that one. Now let's do it the other way on this one. So we have f inverse of this guy. And what was f of x? F of x is 4x plus 2. So now we have to do f inverse to this guy. So everywhere I saw an x, replace it with this guy. 1/4 this guy minus 1/2. Distribute the 1/4. So we have x. 2 divided by 4 is plus 1/2 minus 1/2. Just pops out our x. Therefore, they are inverses. That's all you have to do. Okay, now let's look at some graphs. If we look at f of x equals x squared, so if we look at y equals x squared, and we try and find the inverse, we swap the x and the y. So we get x equals y squared. And so that's what they've graphed here. And so you'll see very clearly in this one, what do you think this line is here? Remember, that is just a reflection over y equals x. So if you take the original function and you reflect it over that y equals x, you get the inverse function. And all I've done here is I've interchanged the x's and the y's. But what I want you to note here is that f of x is a function. But the inverse is not a function. Because remember, in order to be a function, it has to pass that vertical line test that only each input has one and only one output. And you'll see here, for instance, well, this has 2 inputs, so it's definitely not a function, this x equals y squared. However, if we look at this function here, let's see, y equals x cubed, and we look for its inverse, let's say x equals y cubed, because we interchange the x's and the y's. So we get, if we solve for y, we would do the 1/3 power of each side, right? So y equals x to the 1/3 power. And that's what they got here, and that's what they graphed. See, if I tried to solve this one, the problem is, because that's an even power, I would get y equals plus or minus root x. And that's why it's not a function, because I've actually graphed positive root x and negative root x. I've graphed 2 functions that are one right on top of one another. So I know I've just said a lot. If you understood it all, that's great. But if you didn't, what's really important here is that if f is a function, the inverse is not necessarily a function. That's what I want you to take away from this. In this one, g of x is a function, and its inverse is also a function. Now I'm going to look at the same thing we just did, that y equals x squared, but I'm going to restrict the domain. And I'll explain why I'm doing that. So I just want to look for values of x that are greater than or equal to 0. So we have y equals x squared. The inverse, just doing it once more, is x equals y squared. In other words, y equals plus or minus x to the 1/2 power. However, I'm only looking for x is greater than 0. So because we are looking at only x is greater than or equal to 0, we get that the inverse function is just the positive one. And I'm just going to write root x. So now I need to graph them. I'm going to graph f in red. So I only want x values greater than 0. Okay, so y equals x squared. I have 0, 0. If I put in 1, I get out a 1. If I put in 2, I get out a 1, 2, 3, 4. So we know that it's a parabola opening up, but we don't draw this half because, again, only non-negative values of x are holding. So here's f of x. And then let's draw f inverse in green. So here I want to do just positive root x. So I get 0, 0, that's a point. If I put in a 1, I get out a 1. If I put in, let's see, I don't want to put in a 2 because I don't know root 2, but I do know root 4. Root 4 is 2. 1, 2, 3, 4, 2. And so that looks like that. And so you'll see that I just interchanged. This was the point for 2, and this was the point 2, 4. So you'll see that I interchanged my x and y values, right? And just as a quick check if I did this right, well, let's just draw in this y equals x. I'll just dot it. That's y equals x. Well, isn't the inverse, the green curve, just a reflection of that red curve over this axis? Okay, think about just reflecting the red line over this blue dotted line and you would get the green curve. So again, the inverse is just a reflection over that y equals x. Let's do the same thing here. We have y equals x squared plus 2, and I want to find the inverse, so I'm going to swap the x's and y's. X equals y squared plus 2. Subtract 2 from both sides. And now take the square root. So we get y equals plus or minus root x minus 2. In this one, my domain restriction is only non-positive numbers. So since we are looking at x is less than or equal to 0, we just have that the inverse function is that negative 1. Okay, in this one, let's start by graphing f, and I'm going to just make a table of values here. And so let's start with putting in a 0. That's nice and easy. If I put in a 0, I get out a 2, 0, 2. And then I want to put in a negative value, not a positive one, because x is less than or equal to 0. So let's put in a negative 1. A negative 1, the quantity squared is 1. 1 plus 2 is 3. So 1, 2, 3. And then let's put in a negative 2. Negative 2, the quantity squared is 4. 4 plus 2 is 6. 4, 5, 6. And anyway, we knew that this should be a parabola shifted up 2 units, and it is, but we're only drawing the negative x values here. All right, now let me switch to green, and we will draw f inverse. Now I'm going to make a separate table for f inverse. And the reason I'm making a separate table is, look, if I tried to put a 0 into the f inverse function, I have 0 minus 2 is root negative 2, and that's an imaginary number. And any negative x values are just not going to work. So I need some positive x values in this table. Let's think about what I might be able to use. Well, what would pop out as 0 here? if I had 2 minus 2, then I would have root 0, which is something I really like. So why don't we put in a 2 for x, and that would pop out a 0. Let's see what else would make a really nice number. Well, I know the square root of 1, right? So what would make this a 1 underneath it there? If I had x is 3. If I had x is 3, then I would have 3 minus 2 is 1, and root 1 is 1, but I take the negative of it. And what else would be a nice root? Well, we know root 4 is 2. So what would make underneath here a 4? Well, 6 minus 2 is 4. So let's try putting in a 6. That's 4. Root 4 is 2. So we have negative 2. Aha! Look at that. We did, in fact, just swap the x's and y's. You see that? So I didn't actually need to do all that work, did I, to find the F inverse? All I really needed to do was swap my x and y's, and I would have had it without doing any work. Do you see that? All I needed to do was swap these, call this x, and call this F inverse, and go plotting them. See? So I plot 2, 0. I plot 3, negative 1. I plot 6. 1, 2, 3, 4, 5, 6, negative 2. Let's plot it. And then let's do our quick check. Let's draw in y equals x. Yes, indeed. The red curve is just a reflection over that y equals x of that green curve, and it's very obvious in this case. So we definitely did that one right. As we kind of talked about in the previous example, if f of x is a function, it doesn't necessarily mean that its inverse is a function. And one way to tell if the inverse is a function is if it passes the horizontal line test. For f of x to be a function, f must pass the vertical line test. Right? So why do you think I might be saying that in order for the inverse of a function to also be a function, it must pass a horizontal line test? Well, let's think about it. Aren't we just interchanging all the x's and the y's to get an inverse? So if the function has to pass the vertical line test, then the inverse would have to pass the horizontal line test. That just makes sense, right? So in this one, this is f of x. So f of x is a function, and f inverse is also a function, right? Because passes the horizontal line test. In this one, f of x is a function, but f inverse is not a function because it fails that horizontal line test. Another thing that's important is if f is a function and its inverse, we always call that f inverse, right, is also a function, we call that function one-to-one. So a one-to-one function would pass both the vertical and horizontal line test. Okay, so a one-to-one function passes both the horizontal and the vertical line test. Let's consider this function, y equals 3x to the fifth minus 2. Do we think that the inverse is going to be a function? Well, this is an odd degree, right? It's just some transformation of the x to the fifth graph. So yes, the inverse is going to be a function. we think, because again, it's an odd degree. And let's solve it and we'll see that. So in order to find the inverse, swap the x's and y's. So add 2 to both sides. Now I've got to divide everything by 3. Remember, you need to isolate the thing to the power before you go taking roots. So we have 1/3 x plus 2/3 equals y to the 5th. To undo a 5th power, I do the 1/5 power of both sides. So we get y equals 1/3 x plus 2/3 to the 1/5, also known as the 5th root of 1/3 x plus 2/3. Remember that because this is an odd power, I don't need that plus or minus, and that is the reason why the inverse is a function. If, I'm going to do a little aside, I was doing something like f of x equals 2x to the 4th power plus 3, I don't think that the inverse is going to be a function because I have an even power, and let's show ourselves that. When we go to do the inverse, what do we get? We have x equals 2y to the 4th plus 3. Subtract 3. You must isolate that power before going on, so let's divide each term by 2. 1/2 x minus 3/2 equals y to the 4th. When I go to take the 4th root, because that's an even, I need my plus or minus. So I have plus or minus the 4th root of 1/2 x minus 3/2. In other words, my inverse function is equal to plus or minus, and that is why it is not a function, because I have that plus or minus business. It just means that I'm plotting the same above and below. This one, I guess, for final form, I should write f inverse equals the 5th root. And I really think I've answered this question throughout this PowerPoint, so hopefully you can just write a little note to yourself. Look back at the horizontal line test. If I have a function, f of x equals x to the n, can you make any guess as to what values of n will make it so that the inverse of the function is also a function? So just jot down some thoughts and we will talk about it in class.
And that's it for this lesson. Bye.